Here's another statics example. We're going to find find P um, such that acceleration of box A is 1 meter per second squared. So to do that, naturally I'm going to go with free body diagrams. And I'll just start with A and work my way up the ramp. So I'm going to do a free body diagram of A. That's going to be just some facsimile of that box and then the forces that are acting on it. So there's a normal force of the surface, there's a friction force holding it up. That's nothing more than mu times NA. And I've got the pulley, which I'm going to call F sub A, pulling on that. And then I've got mg acting down. I need a coordinate system. I'll match it with the direction of motion. And I note that I'm getting an A up the box, which is 1 meter per second. I think that's everything. I do want to break this guy into his components. That's going to be the mgx and mgy. Now mgx in this case is going to be m box A times g times the x component is going to pick up the sine. So it's going to be sine 30. And gy will then be the cosine. Now I want to do sum of the forces in each direction. Sum of the forces equals m box A times the acceleration of box A. And sum of the forces, this one's x, this one's going to be y. It's 0 because I have no motion in that dimension. This one's going to be easy. It's just NA pointing up minus mg cosine 30 pointing down, and that's equal to 0. Therefore, NA is nothing more than mg root 3 over 2, which is the numeric value of cosine 30. In the other direction, I'm going to have FA pulling up the ramp minus the mgx. I'll write that as mg times a half. That's the numeric value of sine 30. And I'm going to have the friction force. That's going to be mu NA. That's pointing down the ramp. And I think that's going to be all my forces. So that's going to be equal to the mass of A times A, acceleration of A. So I can plug in that N right away. That'll give me FA minus M sub A. I should put the subscript A on the M's since we're always dealing with box A in this case. Mu mg, that's M sub A again, root 3 over 2 equal to M sub A times A. Now I'm trying to solve for the force. Eventually I want to get to the force P, but I'm now at this force F, so I'm going to solve one more step and just bring everything to one side. And one other, well, I'll get this next one as I do the next free body diagram. My next free body diagram is going to be pulley A, the pulley that's attached to A. In this case, I'm going to have two forces pulling up. I'll call it tension sub A, and the force pulling down is F sub A. And again, we'll have the same coordinate system. It's a massless pulley, so that means that this will be mass of the pulley equals 0 or about that, in which case we're going to get 2TA minus FA equals 0, the only direction that has something, or more specifically, TA equals half of FA. I better start labeling the equations. There's 1. This one's going to be 2, so I'm going to be stitching all my equations together once I get there. My next free body diagram, roll up here, give myself space. That's going to be free body diagram of crate B. Again, it's a facsimile where I'm going to have now a force B, that's the pulley on B, pulling up. There's the mu times NB, there's the normal force B. Here's my coordinate system, same coordinate system. So I've got the friction. Now I have to put in the tension A because that other box is pulling on B. I also have acceleration. That's the acceleration of B. By the pulleys, we know that the acceleration of B has to be twice the acceleration of A. And that's a effect of pulley motion. And then we have mg. That is mbg. And again, that's going to be made up of the mbx, mbg in the x direction. Oops, that's going to be y. Fix that. This is going to be mbgy, and this one going down the other way, that's going to be m sub b g in the x direction. So I'll have the same thing in the m b g x direction. Well, that's going to be the sine, so that's going to be m b g over 2. Sine of 30 is a half. M b g in the y direction is going to be m b, and this will be g root 3 over 2, which is the cosine. So now I get to do the same thing as before. Sum of the forces in the x direction is equal to mb, and I can put in 2a there for the motion of box A. That kind of gets me into the same acceleration. It's really the acceleration of the B box. And then the other direction is going to be the sum of the forces equals 0 in the y direction. So again, NB is going to be equal to mg root 3 over 2. It's just the force of gravity. So now I get to do this other side, which is a bit busy. So I'm going to have FB pulling the B block up minus mu NB pulling the B block down, or slowing it down, minus the tension from rope A, minus the MBGX, and the MBGX is going to be MBG over 2, and all that's equal to MB to A. I'm going to roll the screen. Now we can plug in a little bit. We'll have FB minus mu mg root 3 over 2. That gets that term. Minus, I'll just leave this TA there by itself since there's a lot of things to plug in there. And then this will be mbg over 2. That's equal to mb to A. I'm trying to solve for that FB, so I'm going to get it all on one side. This will be TA plus mu mg, this is a b in there, root 3 over 2, that's that term, plus mbg over 2, that's that term, and plus mb to A. Okay, now I have all that stuff for TA to plug in, and note that TA is really going to be FA divided by 2. So I have to go back up here and grab that FA and plug that thing in. It's going to be a little messy. And so I will do that. FP equals 1/2 MA times mu G root 3 over 2 plus G over 2 plus A. That's the TA plus MB times mu G root 3 over 2 plus G over 2 plus 2A. So all of that stuff is now known. A is given as 1 meter per second. I know the mass, I know the coefficient of friction, so really there's everything is known in here. And if you plug all those numbers in, you'll find that FB is equal to about 715 newtons, given what they have. But, roll a little more, there's one more pulley in there. That's a free body diagram of the pulley on B. And in that case, I have this force P, as stated in the beginning of the problem. And I have the FB pulling down, and I have 2 P's pulling up. So by sum of the forces equals 0, because it's a massless pulley, I'm going to get 2P equals FB. So whatever I get for FB, I have to divide that in half to get the P. So therefore, I'm going to have P equal to about 358. And that is going to be what we're considering the answer. Here's an example of using the inverse squared law. Again, the law as I would write it out would be I1 R1 squared equals I2 R2 squared. And that comes, as I might remind you, of I1 being equal to the power divided by angle times R1 squared. So P over 4 pi equals a constant. And that's what leads to being able to equate the I1 R1 squared to I2 R2 squared. In this particular problem, we have our I being represented by exposure being 2 milligrays. So our I1 is 2 milligray at R1 equals 100. And it doesn't really matter what the units are here because the units are going to disappear. So just to make the illustration, I'll leave the units off. And then I want to algebraically manipulate my formula. So I'm going to get I1 R1 over R2. I just divide both sides of my main equation by R2. Square them. That's going to be I2, which is the thing I'm looking for. So here we have 2 milligray. And now the R's are going to be 100 on top, 180 on the bottom. Those are the distances I moved. So I have centimeters on top, centimeters on the bottom. I'm going to square that. So it's 10 divided by 18 squared times 2 milligray. That's going to produce 0.62 milligray. And that's really all there is to calculating that.